Welcome back, students. Today we are doing lesson 15, which is rates of change and behavior of graphs. Rates of change, fancy phrase, it really just means slope between 2 points. And really, we're calculating average rates of change, which again is the slope between 2 points. So we know the slope formula already. That'll make today's lesson a lot easier than it would be if you didn't already know the slope formula. And then behavior of graphs, really, we're just going to be talking about increasing and decreasing and what that means for local extrema, where extreme values are either the highest or lowest points within a given area. All right, so our application we're building up to. Last summer, it was, as it always is, really hot in Phoenix. And so what I did is decided to find something I could do inside where it was nice and air conditioned. So I bought a game called Elden Ring, which is an RPG game, highly recommended, super fun. And it came with the DLC and it cost me about 80 bucks. I ended up spending, this says 90, I ended up spending about 120 hours playing this video game. And so we can calculate how much per hour it cost me to play this game. And we will do that at the end. You're going to see it's very inexpensive. Alternatively, I could have gone out with friends, like on a regular basis, which don't get me wrong, I go out with friends from time to time, and let's say we have four $13 drinks of water with some friends, and that takes about 3 hours. So four $13 drinks of water in 3 hours, I think you can clearly see is more expensive than $80 for 90 hours of gameplay. But we're going to calculate the actual difference in cost per hour, and that'll represent essentially the average rate of change or the difference in average rate of change that we would see on our credit card statements for doing each of these activities. So we'll come back to this at the end and calculate it. But what you're going to learn is that playing video games, although the price of a video game might seem high, if you actually play it, very, very inexpensive. All right, so now as a warm up, rate of change. This refers to how quickly one variable changes in relation to another. So, for example, if you get taller as you get older, we would say that your height increases as your age increases. So increase and increase, those are both positive. So we could also say that the rate of change in your height is positive over time. Because if we have two increases, so increase and increase, one increase refers to we'll call it the output or the y variable, and the other increase refers to the input or the x variable. So if they're both increasing, that means we have positive numbers on top and bottom, and a positive over a positive equals a positive. So that's why we say that the average change is positive over time. On average, you're getting taller. Your height is positively increasing. So, opposite example, when you retire, hopefully you'll have some savings for retirement. And when you retire, that savings will probably go down every year after you retire because you're using it for retirement. That's why you saved it, right? And so we could say that your savings decreases as your number of years since retirement increases. Or we could say that the rate of change of your savings grows, sorry, the rate at which your savings grows is negative while you are retired. Okay, so why is it negative? Well, we have one thing decreasing, which would be a negative change, as another thing increases, which increasing is a positive change. So if we have a negative divided by a positive, sorry, that's the messiest handwriting I've ever put on a screen. So if we have a negative divided by a positive, that's going to equal a negative. And so your money is shrinking, or it's a negative rate of change where it's going down over time. Yeah, there's a whole bunch of other ways we talk about rates of change in real life. So, for example, if you suddenly adopt 40 puppies, the population of puppies could be increasing by 40 puppies per week. Because let's say one week you decided to adopt 40 puppies, guess what? That week, there was a rate of change of 40 puppies per week. A car traveling could be going 68 miles per hour. Where notice over here for puppies per week, I wrote puppies divided by weeks. On the previous screen, you might have noticed cost per hour, I wrote cost divided by hours. A lot of students don't realize this when we first start talking about rate of change, but when we say miles per hour in real life, we really just mean miles divided by hours, and that simplifies to be how many miles we go in 1 hour on average. Same thing with the next one, 27 miles per gallon, just means miles divided by gallons. And that simplifies to be how many miles we go on average for 1 gallon. because once you actually do the division, it simplifies to be over 1. So what I mean by that, I'll show you in this next one. If the amount of money in your bank account increases by $400 per month, it might be that it's going up $1,600 in 4 months, but we calculate that 1,600 divided by 4 to be $400 per 1 month. And then when we express the rate of change, usually we reduce it to be out of 1 month because it's easier to understand. Okay. If I told you 27 miles per gallon, everyone can think, okay, 1 gallon, 27 miles. But if I say 54 miles per 2 gallons, well, then all of a sudden you have to do math. You got to actually divide to try to figure out, okay, what does that mean? So if I say I saved $1,600 in 4 months, really an easier way to say that is I average $400 per 1 month. But based on context, you might prefer $1,600 per 4 months. Because what if you were only going to save for 4 months? Well, you might wonder, how much will I save in those 4 months? $1,600. Okay. But if you want to know on average what you're doing, you always do the division. So we get a 1 in the denominator. Okay. Now, what I want you to do for number 1 is name 3 other rates of change that exist in your everyday life and label them as positive, which would mean increasing, or negative, which would mean decreasing. So I'm getting a little older here. I might be getting +3 gray hairs per week, which would be an increase in gray hairs. Not a good thing. Okay, so positive and increase do not mean good. Let's be clear. All right, -1 headaches per week would be a decreasing number of headaches. So maybe my life is getting better, in which case I get less headaches. Hey, that's a good thing, but it's negative. Okay, so again, good and negative don't have anything to do with each other. Negative just means decreasing, and positive means increasing. All right, and then we could be getting, or my little boy could be getting +1 naps per day, and that would be an increase in the number of naps. So you can see he's over my shoulder right now, taking a little snoozle underneath a portrait of his time in the war. He always gets tuckered out, thinking about, I was working so hard back then, fighting so many enemies, slaying so many nations. It really takes a lot out of him. So he takes naps. And especially when I'm home working, he takes a lot of naps. So I think the +1 naps per day is just from me being present. I like to believe at least. All right, moving on. How do we calculate average rate of change? Well, we already know how to calculate slope from when we learned about linear functions or lines. And so average rate of change really just means slope between 2 points. So if we have the 2 points given to us, such as 0, 1, and 2, 5 in number 2 there, then we just use y2 minus y1 over x2 minus x1, our famous slope formula that we've gotten real good at. If we have a graph given to us, we can just count rise over run, which can be said as delta y over delta x. Delta just means change in. Okay, so change in y over change in x, which again just means rise over run. This is a good way to calculate it when you have a graph and you can easily read the points off of the graph. Okay, but otherwise it's kind of useless if you don't have a graph that looks nice. The first one, change in output over change in input, that's just saying these in words, okay? So that one really doesn't help us much mathematically, but that represents in words what we're doing here. And by the way, I think I forgot to say, these are all equivalent. So we can use any of these at any given time, but depending on the situation, one helps us more than the other. So if we have 2 points, y2 minus y1 over x2 minus x1. If we have a graph, rise over run, or delta y over delta x. And if we have a function, such as in number 3 here, then we want to use f of x2 minus f of x1 over x2 minus x1, which this is really just y2 minus y1 over x2 minus x1, but we don't know what y2 is yet, so we have to calculate it. So we plug x2 into f. All right, so let's go ahead and do this. Number 2 is going to be really easy, just calculating slope between 2 points. We can say that m, the slope, is equal to 5 minus 1 over 2 minus 0, which simplifies to just be 4 over 2, or 2. Okay, so we would say that the slope then, or the average rate of change, so average rate of change, same as slope between 2 points, is 2. Really what we did is we went up 4, right 2, but on average, that's up 2 over 1. So average is out to be up 2 over 1. For number 3, we have to work a little harder. So we're given two endpoints here to our interval, where these endpoints represent x1 and x2. And notice x2 is a variable. What I'm going to do is show you how to plug in a variable real quick and work with that. And then we're going to actually assign a number to t, and we'll see what it simplifies to be. But we're going to do it as a variable first. So in order to calculate, we're going to use the formula at the top right of the screen, f of x2 minus f of x1 over x2 minus x1. We have to first plug in x1 and x2. So f of x1 is equal to f of 0. And if you plug 0 into this function up here, negative 2 times 0 squared minus 1 is just going to be negative 1. So again, negative 2 times 0 squared minus 1, that just equals negative 1. So f of x1 is negative 1. F of x2 is a little bit more boring because we're plugging in a variable. So when we plug in t, nothing actually changes. We just replace the letter x with the letter t. Okay, so we get negative 2t minus 1. Now if we apply the formula, okay, m equals f of x2 minus f of x1 over x2 minus x1. This is going to equal negative 2t squared minus 1 minus negative 1 over, and then we have then we have t minus 0. Okay, so the part in red that I left is our f of x2. That's the most complicated piece of this. And then we have negative 1 was x1, and on the bottom, x2 minus x1. And sorry, I misspoke again, doing that a lot this video. Negative 1 right here is f of x1. All right, so now let's go ahead and simplify this thing. On top, the only thing that we can cancel is we have a negative 1 and a minus negative 1. So this negative 1 and that negative 1 cancel to just give us negative 2t squared. And on bottom, t minus 0 is just t. Okay, so now in later parts of this class, we'll be able to easily simplify this to be negative 2t, because a t on bottom will cancel a squared on top. Okay, so t's cancel. But for right now, what I want to show you is that this is the average rate of change, and now we can plug in a value of t and see what happens. So let's say if t equals 3, okay, so then we would be calculating the interval from 0 to 3. Okay, so right here, instead of 0 to t, it would be 0 to 3 if we make t equal to 3. Then m is going to be equal to, that negative 2t squared over t becomes negative 2 3 squared over 3. Okay, now we do know how to simplify 3 squared on top, 3 on bottom. One of those cancels, but for sake of multiplying it out, up top 3 squared is 9 times negative 2 is negative 18, and on bottom 3, so it simplifies to be negative 6. So what we learned then is that if we don't know what the endpoint is, if we just call it t, then we have this formula negative 2t squared over t. But once I tell you what t is, all we have to do is then plug it in to that formula, and we can get an average rate of change of negative 6. Okay, which means on the interval 0 to 3, it goes down 6, right 1. Down 6, right 1 on average. All right, so now finding the average rate of change from a graph is really easy. It's just rise over run. So if we want to find the average rate of change from x equals 2 to x equals 5, so on the interval 2 to 5, all we do is find the point where x is 2, which is down here, find the point where x is 5, which is up here, and we want to find the slope of the line between them. Okay, so the average rate of change is just the slope between 2 points, and we can just go ahead and count on this graph. We go up 1, 2, 3, 4, and to the right 1, 2, 3. So my slope is going to be up 4 over 3. So the average rate of change is just 4 over 3. If we wanted to calculate that using the formula, then we could use the x and y coordinates. So we have 2, 0 as the first point, and 5, 4 is the second point. So we could do 4 minus 0 over 5 minus 2, which simplifies to be 4 over 3. Or again, we can just count up and to the right because we have nice clean points on the graph, and that represents delta y over delta x, rise over run. All right, so now question 5 says to be constant means to have a rate of change equal to 0, meaning a slope between 2 points equal to 0. And so we want to find an approximate interval on this graph where we have an average rate of change of 0, meaning we have a constant rate of change. Or not a constant rate of change, but an average rate of change that results in being constant. So essentially, we want to find 2 points on this graph that have the same y value. So if I pick the starting point right here, this is 0, 3, and I go directly to the side, then eventually I'm going to hit this point right here. That is approximately 2.5, 3. Okay, approximately, right? It's not exactly 2.5. Maybe it is, maybe it's not, but it's approximately 2.5, 3. So what we did here is we just found that on the interval 0, should have used a bracket there, 0 to 2.5, the average rate of change is 0, meaning we're constant. So imagine this is the number of puppies you own, okay? If you have 3 puppies, and then you get rid of 2 of them, and you get rid of 1 more, and now you have 0 puppies, but then you adopt 3 more. Well, from the starting point to the end point, you went from having 3 puppies to having 3 puppies again. So it's as if there was no change from 0.3 to 2.53. You lost some puppies. Sorry, that really sucks. Maybe you were raising the puppies though and had them get adopted. And then now you got 3 more puppies. And so on this interval, 0 to 2.5, you lost and gained puppies, but in the end, the result is that you have the same number of puppies you started with. You went from 3 to 3. And so that is a constant, okay, because you have the same number you started with. All right. Now, local extrema. A local maximum occurs when a graph switches from increasing to decreasing, and a local minimum occurs when the graph switches from decreasing to increasing. And together we call these local extrema. Okay, so local maxima and local minima together are called local extrema, or local extreme values, meaning these are the highs and lows of the graph. At local extrema, a function is not increasing or decreasing. So imagine you're at the top right here of this little hill. You would have hiked up the hill and then hiked down the hill. But right here at the top, what does everyone do when they get to the top of a pretty hill? Is they stop and they take a picture. Okay, so when you're stopped to take that picture, are you hiking up or down? Well, the answer is neither. You're not doing anything. You're just sitting there or standing there taking a picture. And so at the top of the hills and at the bottom of the valleys, if you're taking a picture, you're not going up or down, you're just constant. Okay, so when we say increasing and decreasing, we don't include the tops and bottoms, the maxima and minima. So if we want to say where this graph is increasing, decreasing, it goes up, and then it goes down, and then it goes up again. So up, down, up. If we write those as intervals, it's going up from negative infinity all the way to this point is -3 comma approximately 4.5. And this other point down here is 0, 0. So it is going up from negative infinity all the way to x equals -3. And then it's going up again from 0 to infinity on the right side of the graph. But in the middle, it's going down. So we would say it's decreasing from -3 to 0 in the middle of this picture. Now notice I use parentheses on the -3s and the zeros. Okay, parentheses on all of these. Because at these peaks and valleys, you are doing nothing. Okay, you're just taking a picture. All right, so now using this increase and decrease in information, we can say what the maximum and minima are. And these are local max and minima, because we're going to talk about absolute maxima and minima in a second. But for local, we have to go from going up to going down or going down to going up. So in this picture, we have both of those. We have a local maximum at x equals -3. That's the point at the top. And a local minimum at x equals 0. Okay, our maximum happens when we switch from going up to going down. And our minimum happens when we switch from going down to going up. Okay, we're going to change that definition now slightly for absolute extrema. The absolute maximum of f occurs at x equals c, where f of c is greater than or equal to f of x for all x in the domain. That is fancy math speak for saying the absolute maximum is the highest point on the graph. So the absolute maximum does not care about increasing and decreasing intervals. It is just the highest point. It doesn't care about anything else, no other rules. It's just the highest point. And the absolute minimum is the lowest point. Okay, so this notation in the middle here, the absolute minima of f occurs at x equals c. So the minimum is at this c value, where f of c is less than f of x. This means the y value of that point is lower than all the other y values. All right, but in English, lowest point and highest point. And we have to check endpoints because the endpoints on the far left and far right might be lower or higher than all the other ones. But it's important to realize that endpoints cannot be local extrema. So for example, this point right here on the left, the graph does not switch from going down to going up. So it does not meet the definition of a local minimum. It is, however, the lowest point on the graph, so it meets the definition of being an absolute minimum. Okay, so that's going to be important when we answer the question right now. Number 7, use interval notation to state where the function is increasing and decreasing. This is increasing from -2 all the way to 0, because the point at the top here is 0, 4, and the point at the bottom is -2, 0. So we start at x equals -2, we go up all the way until we get to x equals 0, and then we go down from that point 0, 4 all the way to this point is 1, 3. So we're decreasing from x equals 0 to x equals 1. Okay, notice no brackets, all parentheses on these things, because when you switch or when you go from increasing decreasing, you are doing nothing at the top of the mountain. There are some textbooks that would say the endpoints should get brackets on them, but other textbooks say otherwise, so that one's more debatable. I would never mark you down for putting a bracket on the -2 here. But on the zeros, on both these, you have to use parentheses. Okay, so both these zeros need parentheses because that is the top of the mountain where you were taking the picture. All right, so now, what are all the extrema? Well, based on the previous slide, we can say that there is a local max at x equals 0. That's the top of the mountain. But because this is also the highest point on the graph, this is also an absolute maximum. Okay, so it's the absolute max because it's higher than all the other points, but it's the local max specifically because it goes from increasing to decreasing. So we don't have a local minimum because this graph never switches from decreasing to increasing. We do, however, have an absolute minimum because this graph has a lowest point at x equals -2 on the left side over here. Now, one other thing that I don't have mentioned here is that it's possible to have no no absolute max or minima. So if we look at the previous graph, notice that the left side keeps going down for forever and the right side keeps going up for forever. So what that means is there actually is no absolute max or min because we always have a lower point somewhere on the left and we always have a higher point somewhere on the right. So it's possible that you don't have absolute extrema, and it's also possible you don't have local extrema. So this second graph here had an absolute max and an absolute min, and it also had a local max, but there was no local min. So you don't have to have one. And up here, we have a local max and a local min, but there is no absolute max or min because this graph goes infinitely far up on the right and infinitely far down on the left. All right, now let's go see how good of a deal Elden Ring was real quick. So if I paid $80 for Elden Ring and got 90 hours of fun out of it, 80 over 90, where this is dollars divided by hours, comes out to about $0.89 per hour. Okay, where dollars per hour is dollars again divided by hours. Now for the drinks, $13 per drink of water at $4, sorry, for 4 of them is 52 total dollars. And it says we had 3 hours of fun there. So $52 divided by 3 hours. This comes out to, if we calculate real quick, 52 divided by 3 is 17.33. Okay, when we round it, $17.33 per hour. Notice much higher amount of dollars per hour. Probably not any extra fun for the record. Elden Ring, great time. But now what we want to calculate is the difference in cost per hour. So difference is going to mean subtraction. So 17.33, that's a 3 over there, sorry, divided by, or sorry, minus 0.89 is going to come out to, let's do math real quick. Our answer minus 0.89 is 16.44. And so the average hour, you are saving $16.44 by choosing to play Elden Ring instead of having some drinks of water with your friends. So now I am not saying don't get hydrated, but what I am saying is video games are way better of a deal than people make them out to be. $80 sounds expensive, don't get me wrong. I'm not saying $80 is free by any means, but if you actually play it, then over the course of the hours you're playing that game, you are saving a ton of money over doing other things that, I mean, don't get me wrong, if the other thing's more fun, go do the other thing. But if you're kind of just doing something because you're bored, I don't know. Think about video games. They're pretty affordable, and you can stay indoors in the air conditioning, which is helpful here in the summer. All right, that's all I got for you guys. That was lesson 15, rates of change and behavior of graphs.